All right, 4.1, we're graphing polynomial functions. So this is Algebra 2, Chapter 4, and let me tell you, this is a large chapter. It's a big chapter. If you start to get behind, it's a really bad thing. So try to stay on top of homework, try to stay on top of notes, and you should do just fine. So we're graphing polynomial functions. Now, some polynomials that we've already graphed before would be lines and parabolas, right? A line, a linear function, is a polynomial. A quadratic, a parabola, a quadratic function is also a polynomial. So those are the simple polynomials that we've done. All right, reading here. A monomial is a number, variable, or the product of a number and one or more variables with whole number exponents. So this would be like the number 5, or x, or 10x, or 5/3 x cubed, or pi x squared. Those would all be monomials. So those are all monomials. So if you think about like the standard linear, right? y equals mx plus b, right? That has two different monomials there. And a monomial is sometimes called a term, two different terms. A polynomial is a monomial or a sum of monomials. So a monomial is a very simple one, and then they get longer. They turn into binomials, meaning 2, or trinomials, meaning 3. So the general rule here, or the general, equation for a polynomial here is a polynomial function is a function of the form f of x equals a sub n times x to the n, and then a sub n minus 1 times x to the n minus 1. And this here is sometimes hard to read, but this is the general polynomial where the a's are the coefficients, that would be like the plain old numbers, and then the x is the variable. This tells us that a sub n can't be 0. The exponents are all whole numbers, and I don't think I've talked about that yet, the whole numbers thing. That means that x to the 1/3 does not work out, which also means that cubed root of x doesn't work out, right? Because x to the 1/3 is cubed root x. So this does not let roots be there, right? These are not allowed to have roots where the x is, right? It could have square root of 2 times x, right? That would be a monomial with a root, but the x is not under the root. Last thing here, it says that the coefficients are all real numbers, right? So we're not dealing with i's, at least not in the actual function. Right here, a polynomial function is in standard form when the terms are written in descending order of exponents from left to right. So that means that you put the biggest exponent first. In standard form of a parabola is like this, where we have y equals ax squared plus bx plus c, right? We have the degree 1, that's the 2, this 2, or excuse me, that degree 2, then we have degree 1, and then we have degree none, or degree 0. Number 1, we're supposed to evaluate. That means to plug in x equals 2. So we're going to plug in f of 2 equals 5 times 2 cubed plus 4 times 2 squared minus 3 times 2 and then minus 7. And I typed that in the calculator and I got 43. And that's all we got to do. We just plug in and we get a number. That means, and what we're going to use in the next example, is that the point 2 comma 43 is on this graph here, right? If we were to graph that function, it would have the point 243 on it. All right, next little blurb of notes. The end behavior of function is the behavior of the graph as x approaches positive infinity on the right or negative infinity on the left. For a polynomial function, the end behavior is dictated by the function's degree and the sign of the leading coefficient. So when an equation is in standard form, it's determined by that first term. So we think about the first term, we have like a times x to the n. And we have a little box that I like to draw. I always think about these as parabolas and lines. So we'll say n is even versus n being odd. So these are the degree here, the n, right? That's even and odd. And then we're also going to have a greater than 0, that means positive. And then we have a less than 0, that would be negative. So for a being greater than 0, looking at this top, the upper left box here, a being greater than 0, so positive coefficient, and n being even, that would be something like a parabola. So I think about a parabola facing like that. Right below it, we have, again, n being even, so still like a parabola, right? Degree 2 would be a parabola. But a is less than 0, that would be a parabola facing downhill. So what we have here is that all polynomials with a positive coefficient and an even degree are going to roughly look like, I mean, it's a big rough. It's not perfect. It's going to roughly look like that parabola there. And what we really care about is the end behavior, those arrows there. The arrows are both pointed up. Down here, we have both arrows pointed down. In the next spot here, we have n being odd. That would be like a linear equation, right? A linear is degree 1, so it's odd. So if a is greater than 0, then a linear equation would be something like this. And if it were less than 0, it looks something like this. And again, these are just rough little graphs to help us remember what it's supposed to look like. So if we look at the top one here, it falls to the left and it rises to the right. Those are some words that we will use: falls and rises. There's two main different ways that I describe these. I describe these using falls and rises, and then sometimes I describe them using the infinity symbols. And I'll show us both of those in the next example. This little blurb here is taken care of in our chart here that I drew. This would be a chart, something that we want to have in our head, that we want to be able to have. We might not memorize it, but we should be able to call the characteristics of the graphs to our mind. So let's look down at example 2. Describe the end behavior of this function here. So this function, we really only care about the leading term, the 5x to the fourth. The degree is even. To have an even degree means that it's going to look roughly like a parabola, right? On the edges, it's going to look like a parabola. And then it has a positive coefficient. And that 5 is called the leading coefficient, the positive coefficient. So if we look back at our chart, we're looking at an even with a positive a. That's going to be the upper left corner. So it rises left and right. Rises left and right. We could say rises left and right. That would be one way to say it. That would be the more maybe informal way to say it. Rises meaning it goes up. The other way, the maybe more fancy way of saying it, let me see if I can change my pen color. We say as x goes left, which would be to negative infinity. As x goes to negative infinity, y goes up to positive infinity. So this would be like rises. And then we could say as x goes to positive infinity, this would be right. Y also goes to positive infinity. That would be, again, that it rises. So we have left and right, and these are some fancy terms to describe left and right on our graph. And then both of these, y approaches positive infinity, that is rising. Both of those means that it rises, it goes up. Now sometimes we can combine these. Because it rises on both sides, we can say that as x approaches positive or negative infinity, y approaches, I can't scroll. Oh, there it is. Positive infinity. So we could combine them to be just one statement if we wanted to, but we don't have to. So there we have it. We have 3 different ways to describe it. We have the first one where it just says rises left and right. Then we have the one in black that's a little bit more complicated. And then the one in orange that's like the complicated one, but kind of condensed a little bit. So those are all talking about end behavior. All right, let's look at this next one here. We're supposed to describe the end behavior again. We have the degree is odd, and then we have a positive coefficient. So that means that it's going to roughly look like a line like that. Right? There's our arrows, and we care about the arrows most. So this is going to fall left and rise right. That would be kind of the informal way to say it. We could also say that as x approaches negative infinity, y approaches, well, as x approaches negative infinity, that's left, y goes down to negative infinity. And then as x approaches positive infinity, so that's going to the right, y approaches positive infinity. So both of these ways, the green way or the black way, are both good. Now we can't write it in the orange way like we did in the last problem because we have rising and falling here, right over here. We have rising and falling, whereas the previous one we were just both rising. So if it's an even function, you could write it in the orange way if you wanted to. Otherwise, if it's an odd function, you'd have to write it in the black way. You'll have to ask me in class which way I prefer for the class that you're in. Sometimes it's the green way and sometimes it's the black way. I'm not going to mark the black way wrong ever, but sometimes it's easier, and sometimes I let you guys do the simpler one, the green one. All right, let's go to number 4. We're supposed to analyze the end behavior again. Our degree is odd, right, because it's 9, and then our coefficient is negative. So for me, you can think about the chart that we had up there. But whenever I do this problem, I always go back, well, the degree is odd, that would be like a line. And then we have a negative coefficient, that would be like having a negative slope. So our line would look something like this. So we're going to rise left and fall right. Now let's write it in the fancier version. As x approaches negative infinity, y approaches positive infinity. That's saying as x goes to the left, it rises. It rises left. And then as x goes to positive infinity, y goes to negative infinity. Again, either of these ways is good. The way on the right is always good. I always like the way on the right more, but sometimes it's okay to do the more simple version, and you need to check with me before you start doing the more simple version. When in doubt, just write them both. All right, number 5, we're supposed to graph this function using end behavior and a t-chart. So let's first off deal with the end behavior. This is a even degree. The degree is even. And we have a negative coefficient. So again, for me, whenever I think about this, a degree being even means he's going to roughly look like a parabola. And the negative coefficient means the parabola is going to be facing down. So this is the picture that I have in my head, parabola facing down. So we want to draw a little coordinate plane, and we're going to have our arrows going down on the left and the right side. Okay. Now we need to decide what goes on in the middle. And what I would suggest you do is you get a graphing calculator and you type this whole function in, and you just get a general look at what is the shape of the chart or of the graph. And after you look at the general shape, then you can strategically choose some points. Now, if you don't have a graphing calculator, that's okay. You just need to check a lot of points. So I went through and I picked out some points: -3, -1, 0, 1, and 2. I was going to try to get the graphing calculator to show up in the video, but I couldn't get it to work out, so I'm having to look at one on the side of me. But these are the points that I decided to plug in. And we're just going to plug them all into, this is a -2, not +2, excuse me. So I'm going to plug all these in. So whenever I plug these in, I got -3 is 0, -1 is 0, 0 is 0, 1 is 0, and then -2 is at 6. Lots of zeros. So let's see if we can plot these. I'm going left 1, 2, 3, 0. -2, 6, 1, 2, 3, 4, 5, 6. -1, 0, 0, 0, and then, oh, that's it. That's our, oh wait, do I have another one? Oh, 1, 0. So there we go. Now we need to connect the dots. So I'm going to start on the left side at my arrow. And let me also say that these aren't perfect graphs. They want to show the general shape, but it's not going to be a perfect graph. We're going to have some humps in here, right? Something like this, something like this. and we're just going to try to get it pretty close. It's not going to be perfect. So I start off at my arrow. I'm going to go through this dot, through that x-intercept. Then I'm going to go up and hit that one up there. Then I'm going to go down, up. Ooh, you know what? We always want to be going through our x-intercepts like that. There, through it, and then there we go. Whenever I looked at my my graph on the graphing calculator, I could see that these were our x-intercepts, and the graph actually went through them. It didn't just, I started to graph in here that it went like this, but it didn't do that. It went all the way through it. Oops, like I had in the orange graph there. I can't erase it. The red piece, ignore that piece. We're doing the orange piece. So always we want to have a graphing calculator next to us. If you have a real, what's the one that I like? The TI-84 plus CE. If you have that one, that's awesome. Otherwise, you can use your phone with the Desmos app, and that works really, really well. All right, that's number 5. Number 6, again, we're going to graph using in behavior and a T-chart. So we're going to draw a coordinate plane. And then let's think about our end behavior. And I'm going to try not to write it all out here. Our leading term is just x squared. That's a positive coefficient and an even degree. So he's roughly going to look like the parent parabola, right? Looking like that. So he's going to go up on the left and the right side. And then we probably need some points to plug in. So the points that I plugged in, this is actually from last year's notes that I'm looking at. I use -2, -1, 0, 1, and 2. And I plugged those into my function, and I got 14, -1, -2, -1, and then positive 14 again. So I'm just going to put a dot up here, and I'm going to say that it's 14 because I don't really want to have to count out 14 different spots. We have the point -2, 14, positive 2, 14, -1, -1, positive 1, -1, and then 0, -2. So he looks a whole lot like a parabola. It's actually kind of like a skinnier version of the parabola. And my arrows here, they aren't going to work out too well for me, so I'm just going to draw some new arrows. And there's going to be my graph there. We want to try to have it be rounded at the bottom. Polynomials in general just have rounded bottoms. This is rounded. And by bottoms, I mean spots where it curves, right? It's not going to be a V. It's going to be more like a U, right? All right, and there's our graph. And what you'll see is that simple, right? This is a very simple polynomial. It just has 2 little terms. The simpler it is, the more plain the graph is. So if we looked back up here, this one, there was a lot of terms. There were a lot of terms. There are a lot of terms. And there's a lot of squigglies in here, right? There's a lot of squigglies in that region right there. The more terms, generally, this is a general rule, the more terms, the more squiggles there will be in the middle of it. The more turning points, the more turns it'll have. All right, let's look at number 7. We're supposed to graph this function using in behavior and a T-chart again. So I'm going to look at my graph, and I'll draw in my little arrows for the in behavior. This is an odd function, or an odd degree rather, an odd degree with a positive coefficient. So he's going to be roughly like a line. So I think about a line going like this. My arrows are going to be up here and down here. And then I typed it in a graphing calculator, right? I just typed this into like the y equals spot. And then I look at a T-chart, x, y. And I want to pick out a few spots. And normally the spots want to be when something interesting is happening on the graph. So look at your graphing calculator and then look and see, is there anything interesting happening? There's some curves happening around the middle of this graph. So I'm going to do -1, 0, and +1. At -1, if I plug that in, I get 2. 0 I plug in and I get 1. And then 1 I plug in and I get 0. So there's my dots there. Now, whenever I'm plugging in, just so you all know what I'm doing, I picked out the -1. And it doesn't matter what points you want to pick here. You want to pick it anywhere that something interesting is happening. And then after I pick out that -1, I plug back into this. So what I plugged in is I said f of -1, oh, that's a 2, -1 equals -1 to the 5th minus 2 times -1 cubed plus 1. So I plugged that in. Now that I have some points out, I look back at my graphing calculator and it roughly has something like that. So that's what I'm going to try to curve in or try to draw in. So I'm going to come up here. It actually turns at this point, and then it kind of, on my graph, it kind of levels off and then it goes back down. It turns like that. So we want to try to incorporate, so right in here, there's some curves happening on my graph. And again, you should graph this in a graphing calculator. If you don't have a physical calculator, then go online and find a graphing calculator. A good one is Desmos. Type in this function here, and it should have some funkiness happening right around the origin here. And we want to try to mirror that whenever we graph functions like this. On homework, on assessments, quizzes, or tests, I'm going to want to make sure that I see a T-chart here. I'm going to want to make sure that you want to make sure that you have one there so that I can give you full credit. Otherwise, it looks like you're just copying from the grapher. And to some extent, that is what we're doing. We're using the grapher to guide our decisions. But that's not all that we're doing, right? We are trying to put in some thought. We have the in behavior there, those arrows there. We have some good solid dots in the middle of it. And then we connected the dots. We use the graphing calculator to help guide us. All right, that is number 7. Let's scroll down, look at number 8. Again, we're graphing with a in behavior and a T-chart. So I'm going to start off by drawing myself a coordinate plane. My in behavior is dictated by the leading term there, the x cubed. So he's a positive coefficient, and he's an odd degree. So he's going to roughly look like a line with arrows on the ends, right? So I can draw in some arrows like that. And then we want to type him in a graphing calculator. And whenever I did that, again, it looked like there was some excitement happening in the middle. And that's going to be a theme also on a lot of these graphs. The squiggles are going to happen very near the middle of the graph. So the points that I'm going to plug in are -2, -1, 0, 1, and 2. And I also want to say you can't be plugging in too many points. And I mean that as in, like, you can always plug in more if you wanted to. If I wanted to plug in -3, that would always be good. It would just make your graph better, more precise. So if I plug these points in, I get -1, 4, 3, 2, and 7. So now we need to plot these points. So I'm going to go left 2 spots and down 1. There's my first dot. Then I go left 1 and up 4. 1, 2, 3, 4. Then 0, 3. 1, 2. And then 2, 7. So it's 4, 5, 6, 7. So now we could just kind of try to connect the dots. So I start off at this arrow down here. I go through that point. I have to touch the x-axis. I turn there, turn back. I'm coming back up. So I should probably take off this and say that it goes down faster. And there we go. That's our graph. Again, we're looking at a graphing calculator. We're trying to use it to help guide our decisions, but we are putting some thought into how this works. If you don't have a graphing calculator and you don't have a phone or anything that you're able to get on the internet with and graph this with, then you'll just need to use a lot more points. I'd probably say from like -5 to +5. And that would help give you a good estimation of what's happening in this. And that could work on any of these graphs. If you don't have a graphing calculator, just plug in a lot of points. Later on in chapter 4, we're going to have some better guiding decisions for how we can choose where our turning points are. So why is there a turning point there and there, like where it changes directions? We're going to have some better, more rigorous ways to decide if it turns or if it just goes through a point. But for right now, we're going to use the graphing calculator to help guide us. Scrolling down, and that is it. So that is section 1 of chapter 4.